There's been a lot of talk lately that concerns me, primarily because, in my opinion, it is very misleading to most people that hear it. That Earth may be disposable, that we cannot save it for the future of humanity. Basically, throw Earth away, travel to another planet to inhabit, and in that way, secure the future of the human race. There are some of the most influential, wealthiest billionaires who actually believe that it is possible and are spending millions, if not trillions of dollars to achieve this. Really? Abandon Earth and move the human race to a planet that has no atmosphere, is extremely cold, is not shielded from cosmic rays, radiation, or the solar winds, and has soil that is poisonous? Are you ready to rethink the stories you've heard about our destiny beyond Earth and to look closely at the actual science shaping our cosmic boundaries? Is Mars our next Earth? Many people have the growing belief that Mars is destined to become our emergency refuge. In this video, I'll explain why this is a fantasy, an illusion, and why it is physically, biologically, and logistically impossible. Mars isn't simply another landmass. It's an entirely separate world. And the obstacles aren't just more difficult. They are unlike anything we've ever encountered. So let's get started. Elon Musk has publicly stated his goal is to place 1 million people on Mars by the year 2050 and create a self-sustaining civilization. Think about that for a moment. 1 million people by 2050. That's only 25 years from now. Here are the logistics of moving 1 million people to Mars in that amount of time. The largest rocket currently in development is SpaceX's Starship, which is designed to carry maybe 100 people per launch. 1 million people divided by 100 people per launch equals 10,000 launches. To achieve 10,000 launches in 25 years would require 400 launches per year, meaning at least one launch per day, every day. And remember this, each launch requires months of preparation, perfect weather conditions, precise orbital mechanics, and enough fuel to accelerate a massive spacecraft to interplanetary velocities. How about if we begin by trying to understand the time and risks involved for that type of journey? Mars's orbit is, on average, 139,808,518 miles from Earth. Now, I use the word average because we have been led to believe that orbits are circular, when in fact they are elliptical. When Mars is nearest to us, it is roughly 34,175,415 miles away. That's when it's at its closest and offers the only reasonable time to launch a spaceship to that target. At its most distant, it is 248,548,466 miles, because now it's on the opposite side of the sun than we are. What this means is we cannot travel there whenever we choose, but rather we would only launch when Mars is closest. That alignment happens only once every 26 months. The quickest spacecraft we have ever sent past Mars was NASA's New Horizons, which flew by at 36,000 miles per hour on its way to Pluto. But even at that astonishing velocity, the trip would still exceed 30 days to reach Mars, even when it's at its closest point. And we don't currently have the technology to send a spaceship at that velocity. The fastest speed ever achieved by a crewed vehicle was Apollo 10, reaching 24,791 miles per hour during its return trip from the moon on May 26, 1969. That record has yet to be surpassed. Okay, so we send the spaceship, along with its crew, at a relatively slow speed of 24,000 miles per hour. But here's the limitation. A mission to Mars carrying astronauts would require enormous quantities of fuel. It would require life support, provisions, and radiation protection, and all that additional weight would force the spacecraft to travel much, much slower. Current projections by NASA suggest the travel time would be approximately 9 months. During this time, the astronauts would be confined within a metal shell, exposed to cosmic radiation, boredom, and mental stress, while at the same time, despite any exercise that could be performed, their bones would weaken and their muscles would atrophy with every passing day. Cosmic radiation is only one of the many issues that would have to be dealt with during the 9-month space travel. But the people don't have to worry, you might think. After all, they're protected from the radiation by the metal hull of the spaceship. No, that's not how radiation works. Nothing completely blocks all solar radiation in space. And there are more than a few types of radiation, galactic cosmic ray being the hardest to stop. Okay, so use lead. We all know lead stops X-rays. Well, there are two problems using lead to block radiation in a spaceship. First, it's heavy. Weight management is a prime consideration on any spaceship. Lead creates a secondary radiation referred to as Bremsstrahlung, braking radiation. These are high-energy X-rays generated when fast electrons rapidly decelerate by the lead's density, potentially creating a more penetrating and hazardous radiation source than the original beta radiation particles. To block galactic cosmic rays in a spaceship, the best choice would be hydrogen-rich materials like polyethylene or water liquid hydrogen, mainly because they are light elements that could be used for passive shielding. In addition, water is needed for the space travelers, and hydrogen can be used for rocket fuel. So that may be a reasonable option. So let's say we survive all the issues with space travel, particularly extended space travel, and the ship actually reaches Mars, makes a soft landing, and remains intact. Now, landing on Mars is a complicated endeavor for another video. According to Elon Musk, robots were already there and had begun construction on habitat. But that is also a subject for a later discussion. So what's the first threat people would encounter when they step from the spaceship onto the Martian surface? Radiation. Earth's magnetic field and thick atmosphere shield us from the relentless stream of cosmic rays and solar particles. Mars lacks a global magnetic field and possesses an atmosphere only 1% as dense as Earth's. Each day spent on Mars would roughly equal an X-ray every other day, which, over a relatively short time, would damage DNA, increase cancer risks, and produce organ failure. Let's say with future technology we overcome the radiation issue. Then comes the next problem, the atmosphere, or rather the lack of one. Mars has essentially no breathable air, and atmospheric pressure is so low that without a pressure suit, your blood would literally boil. A radiation-proof suit would be required each time you set foot on the planet's surface. Basically, the entire planet is a vacuum chamber compared to Earth. The next problem is gravity, which is only 38% of Earth's gravity. That's 62% less than the gravity on Earth. Sure, it'd be a lot of fun to be able to jump hundreds of feet, but what effect does this diminished gravity do to a human body? The human body has evolved for Earth's gravitational pull over millions of years. Our entire system relies on Earth's gravity to function correctly. On Mars, astronauts lose about 1% of their bone mass each month due to the lower gravity. Even with strict exercise, there would be significant muscle and bone loss after less than a year. In addition, after years spent there, your bones could become so fragile and your muscles so diminished that coming back to Earth may be physically impossible. The growth of bones, muscles, and our cardiovascular system all depend on Earth-level gravity. What could be another problem, assuming we overcome these first obstacles? What about food? A civilization on Mars would need to find a way to regularly produce food for the colony. No problem, one might think. Just fertilize the soil and plant the seed. Nope, that won't work either. Mars doesn't have a functioning ecosystem. No plants producing oxygen, no nitrogen cycle, no carbon cycle, no food webs, nothing. Every calorie of food, every breath of air, every drop of water needs to be manufactured and maintained through technological systems that cannot fail, not even for a few hours, without killing everyone. Okay, so we build something like a greenhouse, protected from radiation and kept warm enough to grow plants, because remember, Mars is quite cold. First, Martian dust is as fine as talcum powder. Its grains are unbelievably tiny, only about 3 micrometers wide, which are small enough to travel deep into the lungs and carry an electrostatic charge that would cause it to cling to anything it touches. So each time you entered a habitat after a walk on Mars, you would carry this hazardous dust inside with you. It would gather in your living space, your tools, and your lungs. It's like trying to survive in a place filled with poisonous talcum powder that also behaves like a magnet. But the most dangerous part is its toxicity. The soil on Mars contains naturally occurring percolates, which are highly soluble, toxic chlorine salt compounds. Their presence complicates life support, food production, and water use due to their oxidizing nature, and have the potential of disrupting thyroid function, hormone production, and plant growth. This would require high-intensity removal methods to detoxify the soil. So here's the next problem. As I mentioned a few moments ago, Mars is extremely cold. This thin atmosphere also prevents Mars from retaining heat. At the equator during summer, temperatures might climb to a pleasant 68 degrees Fahrenheit at midday. But by nightfall, the temperature plunges to a minus 100 degrees Fahrenheit. At the poles in winter, it becomes so cold that carbon dioxide freezes out of the air that reaches temperatures of more than minus 190 degrees Fahrenheit. These drastic temperature shifts occur each and every Martian day. Well, next, let's consider the cost. The Apollo program from 1969 to 1972 would cost in excess of $350 billion in today's currency. Missions to Mars would be vastly more expensive. Cautious estimates place a Mars program in excess of $1/2 trillion today. And that's just for the initial mission. And that's only travel. It doesn't include housing, life support, food, water, or any of the infrastructure required to stay alive on Mars. Building a self-reliant settlement would demand tens of trillions of dollars over many decades. Let me say that again. Tens of trillions of dollars. The technological obstacles multiply rapidly. Reaching Mars is only the beginning. You must also create everything necessary to endure life there. You need to generate fuel for the return trip, meaning you have to build a chemical factory on Mars. You need to repair and maintain equipment, which requires producing tools and replacement parts. You need to expand living areas, which calls for creating construction materials. Each of these tasks requires specialized machinery transported from Earth or constructed on Mars entirely from scratch. The Martian air is 95% carbon dioxide, which might sound ideal for plants, but it is poisonous to humans at those levels. To grow food, you would need enormous greenhouses with controlled air heating for the bitterly cold nights and artificial illumination to compensate for the faint sunlight. Those power demands alone are overwhelming. Solar arrays on Mars generate less than half the electricity they would produce on Earth and would be continually coated with layers of dust, which would require substantial maintenance to keep them performing at their maximum level. Nuclear reactors would become essential, and transporting nuclear materials carries significant dangers as well as geopolitical complications. In truth, colonizing Mars would be the costliest project in human history, consuming resources that would resolve every issue on Earth many times over. The trillions of dollars needed just to establish a basic settlement on Mars could deliver clean water to everyone on Earth, eliminate malnutrition, cure numerous illnesses, and still provide funds to improve education and rebuild infrastructure. The myth of Mars colonization diverts attention from the actual emergency confronting humanity right now: climate instability, vanishing species, inequality, global disease. These issues can be solved, but they need the same resources and focus currently being wasted on Mars fantasies. Imagine if the tens of billions of dollars that are currently being spent on Mars colonization fantasies were instead invested in developing better solar panels, more efficient batteries, and smarter electrical grids. Imagine if the research teams working on artificial general intelligence were instead focused on developing AI systems that could optimize renewable energy distribution, accelerate scientific research, or improve educational outcomes for children around the world. Imagine if the entrepreneurs obsessing over tremendous AI advances were instead working on treatments for Alzheimer's disease, depression, and other conditions that we now contend with. We could make genuine progress on problems that matter using technologies that work within time frames that are actually achievable. We're delicate beings who require a remarkably narrow set of conditions to live. Mars isn't merely outside our comfort zone. It lies far beyond our survival range. The challenge isn't fleeing from Earth. It's proving ourselves worthy of calling it home. The red planet will remain what it always has been, an exquisite point of light in the darkness, a destination for robotic explorers, and a reminder that across the immense expanse of the universe, there is nowhere quite like here. Our destiny isn't waiting somewhere among the distant stars. It's rooted on this pale blue dot that Carl Sagan spoke of, and is the only home our species has ever known. That truth isn't a restriction. It's an invitation to make our planet everything it was meant to be.